Whoa. Hey guys, I'm here. Let's get technical. Recently, I got this curiosity box by Vsauce, and in it came these little beads. These are polymer beads that grow up to 300 times their size when you put them in water for 12 hours. I don't have enough space on my SD card for 12 hours. Anywho, I could talk about the science behind why these beads get so big, but what I think is even more mind-blowing is how they become invisible underwater. Now you see them? Now you can't. What? Okay, I put a ball in one of these bowls. Can you tell which one it's in? Vote by clicking the eye in the upper right-hand corner. Okay, here's the answer. Psych, there's balls in both. You just got bamboozled. Today, let's get to the bottom of why these balls disappear under the invisibility cloak of water.
What is it? Some kind of cloak. Well, let's see then. Put it on. Whoa!
Well, it isn't magic. It's science. Here, let me give you a hint which will help you find out why this happens. Check this out. If I stick this straw through the ball like this, then you can see that the ball kind of distorts the straw a little bit. But if I take the straw and put it back in the water, the distortion disappears. Okay, so that's a bit of a hint, but to actually start answering this question, we must take a look at why the straw looks distorted in the first place. You ever notice that? When you put a straw in water, it looks really weird. What? This occurs because light travels at different speeds through different mediums. Think of it this way. Let's imagine that I'm running. Well, just imagine. Oh, come on, it's not that hard. Let's imagine that I'm running a 5K with my friends, and we're about to reach the finish line. Because we're rebels and took a shortcut, we're coming at the finish line at a weird angle, and because of that, we stop running and start walking at different times. Oh, and we're holding hands. That's actually very important. The person on the very left is the first to slow down, and then the next person slows down, and then the next, and the next. Because of this delay in slowing down, the angle of the line perpendicular to the line of people is changed. Think about it. Because this person is now going slow, this person is going faster than him, and they're linked together, the entire line starts to shift to the left until eventually everyone crosses the finish line and slows down. And this also works if you look at it in reverse. If we go from walking to running instead of running to walking, the new trajectory is closer to the x-axis than the y-axis. Also, I want to point out that if the group is in just a straight horizontal line and not on a diagonal line, there would be no change in the angle of trajectory. And you can try this at home too. If you're ever with a group of friends and want to try this out, set up a finish line, link arms, and then realize that as each of you pass the finish line and start to slow down, you change direction. So how do people gallivanting along relate to a straw and a glass cup of water? Wow! I just said the weirdest metaphor I've ever said on this channel! And remember, I compared fidget spinners to Dumbledore at one point, so essentially, the same effect is happening here, but instead of people running, it's light. Using the same logic, as light travels from air into water, it's bent, making the straw seem bent. But Alex, if the straw becomes bent because the light going from the air into the water is bent, then why does the straw in water look like it's the same angle as the straw outside, but it's just like cut off and moved over a bit? What? That was quite possibly the greatest sound effect I've ever made. What? Okay, troll. As much as I want to be mad at you for not watching the whole video, I'm actually legitimately impressed that you're paying attention. Congrats, 5 points to Gryffindor. Well, remember, light changes mediums twice. Once when it goes from air to water, and then once again when it goes from water to air in order to get to your eye. That second medium change causes the straw in the water to be at the same angle as the straw outside the water, but it also causes that offset. Also notice that the steeper the angle you tilt the straw at, the more extreme the offset is, and when you put the straw straight up, there's no offset at all. Remind you of something? This whole effect can be modeled with diagrams like these, which physics students are very well aware of, as well as an equation, Snell's law, which looks like this. Snell's law states that the index of refraction of the first medium multiplied by the sine of the angle of incidence of the light ray is always equal to the index of refraction of the second medium multiplied by the sine of the angle of refraction. To help you remember Snell's law, here's a rap. It is this. That was real helpful. Well, probably about half of you are super familiar with this equation, the other half probably isn't, and don't worry, the equation itself isn't that scary, and you don't really need to know all of it to help us in this case. Oh, now I get why most students are dissatisfied with the school system. But hold up, wait a minute. All good, just a week ago. Crew, at my house, and we party every week or so. But seriously, hold up. I mentioned the index of refraction, but what is that? Well, you know how we established that light travels at different speeds in different mediums? That's where the index of refraction comes in. The index of refraction is the speed of light in a vacuum divided by the speed of light in a medium. So in air, where the speed of light is basically the same as in a vacuum, the index of refraction is just a tiny bit more than 1. In water, where the speed of light is a lot slower, well, relative to air, the index of refraction is higher, about 1.33. Essentially, the slower the light moves through a medium, the higher the index of refraction. Now is a good time to go back to one of the first things I said in this video. These are polymer beads that grow up to 300 times their size when you put them in water. Man, I was so young back then. So naive. But seriously, when the beads soak up that much water, they basically turn into water. 99% of one of those beads is H2O. This makes these balls have a very similar index of refraction as water, since because it soaked up so much water, light travels through them at practically the same speed it would travel through water, thus making their index of refractions almost equal. And if we go back to Snell's law, if the two index of refractions are equal, then that means that the sine of the angle of incidence and the sine of the angle of refraction must be equal, which means that these two angles must be equal, which means that light isn't bent when it's traveling through the beads, which makes them invisible! We did it, Reddit! Now is a good time to note that the two index of refractions aren't exactly equal, which is why you can still sorta kinda see the outline of the balls if you look closely. If they were exactly equal, then they would be purely invisible, like pouring water into water. However, these balls are close enough. So, in conclusion, these balls become invisible underwater because they have practically the same index of refraction as water, which means that light treats these balls and the water as basically the same substance. Thanks for watching, DFTBA, explore on. There are still balls in there, okay. If you got this far, then you probably love mind-blowing physics, so if you want to see more, check out this marshmallow experiment. It's pretty sweet. No, thank you. No, thank you. Please click.